Doesn't look like. I don't see.
It seems that our presenter is not here, therefore, we will be moving on to our next presenter. Our next talk is Machine Learning Driven QSAR and Docking Pipeline for Identification of Amyloid Beta A4 Inhibitors in Alzheimer's Disease, presented by Sohith Reddy. We invite you to begin. Once again, all the presenters are advised to turn on their video cameras for the presentation. Thank you.
Yeah, am I visible? Am I audible?
Yes.
Yeah, oh, thank you so much. So, hi, my name is Sohit. So, today I'm going to present about my very own project, which is machine learning driven QSAR and docking pipeline for identification of amyloid beta A4 inhibitors in Alzheimer's disease. So, basically, overall, we are leveraging the power of machine learning in order to predict the probable inhibitors in order to cure Alzheimer's, like for a proper therapeutic strategy. So the main agenda which I'll be covering in this session is going to be introduction and the workflow which we have implemented along with the results and discussion, and we'll conclude the session. So, Alzheimer's disease. So basically it's a chronic neurodegenerative disease that leads to gradual loss of neuronal cells. So it is the causes for around 60 to 70% cases of dementia. So pathologically it has two main hallmark features, which is extracellular amyloid A beta plaques or intracellular neurofibrillary tangles. So in this study, we are focusing only on extracellular amyloid plaques. So how is this formed? So basically, there is a protein called amyloid precursor protein called APP. It's a transmembrane glycoprotein that is predominantly expressed in the brain. So basically, it undergoes two pathways. One is amyloidogenic and another is non-amyloidogenic. But in this study, we are just focusing on amyloidogenic because when this protein is cleaved by two proteins, which is beta secretase and gamma secretase, so this abnormal cleavage results in the formation of amyloid beta peptides. So what this amyloid beta peptides does is they aggregate the form of senile plaques. So if we target this amyloid beta A4 protein, then it could inhibit the plaque formation and enhance clearance. So that is our main key strategy for disease modification in Alzheimer's disease. So currently, Alzheimer's targeted therapies are mainly focusing on this specific protein, and that's why we are currently targeting this protein right now. So, if we talk about the workflow, so we have used the database called Campbell database. So, it's predominantly the UK's database. So, we have taken the data set from the Campbell database, which has all the bioactivity data of amyloid beta A4 inhibitor. So when we collected the data, so it had around 8,968 bioactivity data points for around 1,498 compounds overall. So for these compounds, the bioactivity for all those compounds is usually measured by IC50, inhibition concentration. And then from that, we have curated the data, like we selected data which had only IC50 value. We do not want the other molecules which do not have the IC50 value because it could hamper our workflow. So from 1,498, we came down to 1,256. And then from those compounds, we removed the compounds with redundant and missing bioactivity values, and it resulted in a curated data set of 1,246 compounds. And then we label the compounds as active, inactive, intermediate. And then this is the overall pre-processed data set we are having, which is of having 1,246 compounds. And then we did some pre-processing where we have calculated Lipinski descriptors. Lipinski descriptors are basically determines the drug likeliness of a compound, molecular weight, number of hydrogen donors, acceptors, and log p values are very critical important features. So we have calculated those descriptors for all these 1,246 compounds, and then for our easy conversion from IC50, we converted those values into PIC50 values and removed the intermediate bioactivity class. And then we got an overall process data set of 1,241 compounds. So from that to 1241 compounds, we applied Kenneth Stone algorithm to identify the diverse compounds and then checked with our machine learning algorithm and also verified using docking. So this is the overall pipeline which we have devised. So if we actually look at the data with our 1241 compounds, so if we look at the clustering of inhibitors, they're basically ranging in the molecular weight anywhere between 200 to 600 Daltons, and the log P is anywhere ranging from 2 to 7. All right. And then when we talk about the Lipinski rules, so in our data set, basically log P should be less than or equal to 5 according to the Lipinski rule. So if you look at the data, the inactive and the active data set is actually balancing anywhere near to 5. But there are some outliers here and there. You can see 10, 12 and all. So it is very important for the machine learning model to also identify those outliers as well. So that's why we have considered them. So similarly, we have number of hydrogen bond acceptors, which should be less than or equal to 5, and then it should be less than or equal to 10, and then molecular weight should be less than or equal to 500. So this is to visualize how the data set is looking like, how much inactive and how much active and inactive in our data set. And now so we compared all the machine learning models. So we took in our hand around 40 machine learning models. We just not pinpointed like only 4 algorithms we're going to compare, but we took overall 42 machine learning models into consideration, and surprisingly we got histogram gradient boosting regressor as a top performer. So how do you determine whether a machine learning model is performing well? So a machine learning model should have a higher R square, a lower RMSE, and a lesser time efficiency. So basically this higher R square can be seen in histogram gradient boosting regressor, and lower RMSE as we can see, and then the time is anywhere to 1. So basically we can still consider that because considering the amount of R square it is producing. So we took the histogram gradient regressor, and then when we did the plotting whether what is the experimental data versus the predicted data, you can see that most of these values align across the diagonal, which means the model is able to distinguish between active and inactive very well. So what are those features that are making the model express it correctly? So when we did some permutation importance, we found out that these are the top fingerprints that are making the model effective to make the decisions correctly. So as I've told at the starting, we have considered a Kenneth Stone algorithm to take 30 diverse compounds, inactive, intermediate, and inactive. So it has these red are the diversity set and these are the active inhibitors. So this algorithm has picked out certain inhibitors of 30, and then we did some docking analysis. So these are the top 3 compounds that are exhibiting the best result. So this is the website which we have devised, NeuroIC50.streamlit.app, which I can show you right now. So here, this is a website which we devised. So basically you input your molecule in the form of smiles, and then you give your Campbell ID, the database source, and then our machine learning model, which is histogram gradient regressor, it will analyze and give you the PIC50 value, which is the predicted bioactivity. So I have a saved text file, so I'm going to show you. So I'm going to upload over here, and then I'm going to start predict. So these is our input value, which is in the
Thank
form of
you for presenting your research findings with such clarity and depth. To stay on schedule, we must now conclude this session. We encourage to your enthusiasm. We may now move on with the question and answer session.
yeah, sure.
Okay, can you summarize your study a little bit?
Yeah, sure. So basically, we have devised the QSR model. So basically, it's a machine learning model. So basically, for Alzheimer's, the crucial target is amyloid beta A4 target. So for that target, we have a lot of inhibitors in our database. We need to get the best out of them. So in order to get the best out of them, we need a better machine learning model. So we took histogram gradient regressor model, and that performed really well. So we're just not trusting machine learning, but also validating using molecular docking. So the binding energies were greater than -6, so which is really good. So we anticipate that the guidelines which we have devised in this overall workflow could be beneficial for designing novel inhibitors for this disease. Yeah, thank you.
Can you show the slides which talked about the time taken? What was the time taken?
So the time taken here, you can see it's somewhere around 0.8 to 1. The histogram gradient boosting regressor.
0.8.
Yeah.
What did you say?
So 0.8 seconds.
Seconds.
Yeah.
So that was the time taken.
Yeah. So the time taken.
Any significant data?
Any significant?
Yeah, the p-value and the other values.
So
There is
basically, we are not considering the
significant.
p-values over here. We are considering the R-square and RMSE. So R-square
Okay.
basically gives you the overall idea, the proportion of variance that could be explained. So the variance could be explained better with 0.62 with histogram gradient boosting regressor. And RMSE is basically gives you root mean square error. Basically, it gives you the difference between the actual value and the predicted value. So here you can say it is less than 0.5. So which is
Yes.
basically a good thing. So that's why.
Good. Yes. Okay, thank you.
Thank you so much.
Yeah. I have a few suggestions as I mentioned earlier for the first presenter as well about the citations. So the one you mentioned in the introduction part, like you said that the Alzheimer is the chronic degenerative disease, and 60 to 70% of the Alzheimer diseases are dementia cases. So where did you get the statistic? So we just want to put the citation so that we can show the audience that this is the where you get this information.
Oh, sure. I'll put that.
We have the different types of the citation. We main two things are Vancouver and other citation. So you have to make sure which one you would like to use. Okay?
Yeah, sure.
So the other one is the one you present is very nice. So especially you compare the data collection and then the model, QSAR modeling, right? So I just want to suggest, why don't you just use the same bigger font so that we can see more clearly.
So you want to see
Font.
website?
No, I mean the font, because
Font
we can
size.
clearly see the one you compare data collection and then your QSAR modeling. So make it more visualized, you should maybe increase the font size.
Oh, all right. Yeah, thank you.
Okay?
Yeah.
Yeah. That's all from my points. Thank you.
Yeah, thank you so much.
A truly impactful application of machine learning in healthcare. Thank you. Let's move forward with our fourth presentation.